So in this video lesson, we're going to have a look at electricity, and we're going to talk about a couple of different concepts with electricity. So we're going to start with just the fact that electricity is the flow of electric charges. Okay, and specifically, that is the flow of our electrons, which are negatively charged. Versus the flow of protons, which are positively charged. Because we know that protons don't leave the nucleus of an atom, but electrons are able to move back and forth between different atoms. And so electrons can flow through wires and lots of other objects as well. And so that's their definition for electricity, is the flow of electric charges, mainly the flow of our negative electrons. All right, so the symbol for charge, so electric charge, has a symbol in physics, and it's either a capital Q or a lower q. It could actually be either. Both of them are fine, and it is a scalar quantity. Okay, meaning it has absolutely no direction associated with it. So electric charge, nope, just randomly put a Y in there. Electric charge is a capital Q or a lowercase q, and it's a scalar quantity, so no direction associated with it. The unit, hold on, we got to get rid of this U. There we go. So the unit for electric charge is actually the coulomb. And the symbol for coulomb is a capital C, okay? And the coulomb is a new base unit or fundamental unit, and it's the unit for charge. And so anytime we're talking about how much electric charge something has, we say it has so many coulombs of charge. All right, now one electron actually has a charge of negative 1.6 times 10 to the negative 19 coulombs. Okay, so one electron doesn't have a charge of 1 coulomb. One electron is actually the charge of 1.6 times 10 to the negative 19 coulombs. Okay, and that's just a defined value. So every electron is defined in that very specific way. Of course, it's a negative, all right, but it is not -1. So when you're first learning about electrons and protons in the atom, we talk about how a proton has a charge of +1 and an electron has a charge of -1. And that is true in comparison to each other. Okay, but the actual unit of charge for an electron is negative 1.6 times 10 to the negative 19 coulombs. Okay, what that means is also that one proton, so if you have one proton is actually positive 1.6 times 10 to the negative 19 coulombs. And so they do actually have the same amount of charge, right? They are 1 to 1. One is positive, one is negative. But when we're talking about how much their charge actually is, when we're talking about it in the units of coulombs, it's 1.6 times 10 to the negative 19. Okay. Now, if we want to calculate the charge on an object, okay, so Q is equal to N times the charge of our electron, okay? And so N is going to be the number of electrons there are, and the E minus is the charge of one electron. Okay, so that's our constant value, all right? And so if we have 25 electrons, let's just try an example here. So we have 25 electrons on an object. So what's the charge? So if we have 25 electrons on an object, we want to know the charge. We're going to do 25 times our 1.6 times 10 to the negative 19 coulombs. So we're just going to do that on the calculator. And so that's going to give us a charge of negative 4.0 times 10 to the negative 18 coulombs. Okay. There's no need to put the negative charge in with the charge on an electron, only because if all you have on an object are 25 electrons, then you're going to have a negative charge on that object. Okay, so that object has to be negatively charged because it only has those 25 electrons. All right. So since we're going to be working with the Coulomb and we're working with objects that tend to have really small charges, I just want to remind you of our small scales. So if we want to use numbers that are much less than 1, remember that we want to use some of those small scales. So I want to remind you that the milli, which we use a little m for, is 10 to the negative 3. That the micro, which we use the Greek letter, right? Mu is 10 to the negative 6. Nano, which we use a little n for, is 10 to the negative 9. And then pico, which is use a little p, is actually 10 to the negative 12. Okay, so just like when we're using those larger units like mega and giga, we also could now be using some of these smaller units like milli, micro, nano, pico. And so you want to keep that in consideration. The most common one is that we would use millicoulombs. So if we have, say, 25 millicoulombs, okay, you want to keep in mind that that means that we have 25 times 10 to the negative 3 coulombs, okay? And so you want to keep that in mind because we're going to use millicoulombs frequently for charge. And so you want to be able to convert into coulombs appropriately because anytime we're using calculations with charge, we're going to want our unit to be in coulombs, not in millicoulombs. All right. So we're going to start talking about different parts in a circuit. And so the first thing that I just want to remind you all the way back from grade 9 is I want to remind you of what a series circuit looks like and what a parallel circuit looks like. All right. So in a series circuit, there is one pathway for electrons to flow. In a parallel circuit, there is more than one pathway. Okay, so in a series circuit, we might have our battery. And we're going to put an open switch in here. Then we're going to go back to the battery and we'll have our light bulb in here. Okay, so in a series circuit, we have just one pathway for electrons to flow. So the electrons are able to flow through the circuit, but there's only one pathway for them to come from the battery and then to go back into the battery. There's only that one pathway for them to follow. In a parallel circuit, there's going to be more than one pathway. Here, we'll put an open switch in this one too. So in this parallel circuit, we can have the electrons flowing through and they can go through this first light bulb and then back around to the battery. Well, let's actually put bulbs on here. And or they could flow through this second light bulb and then flow back into the battery. And so there are two separate, distinct pathways that the electrons can travel through in a parallel circuit, okay? So in a series circuit, there's only one pathway. In a parallel circuit, there's more than one pathway. So there could be two pathways, or there could be three, or there could be six. Depends on how the parallel circuit is put together. But there are more than one pathway for the electrons to get through the circuit. And you'll notice that if the electrons pass through this light bulb, the first one on the left, they don't have to pass through the second light bulb, which means electrons can pass through either light bulb, but they don't have to pass through both light bulbs to get back to the battery. And so electrons likely will not pass through both. Electrons will pass through one or the other. All right, so there are three things for us to talk about in terms of a circuit. And so there is current, there is voltage, and there is resistance. Okay, and so we're going to talk about each of these three things separately, and then we'll bring them back together and talk about how they're related to each other. Okay, but we're going to talk about current, voltage, and resistance when we're looking at these series and parallel circuits. Now, how current, voltage, and resistance happens in series circuits versus parallel circuits is slightly different. So there's some different rules that go along with both of them. So we're going to start with electric current. Okay, so we're going to start by talking about current. All right, so electric current, the best way to think about this is it's representing the electron flow. Okay, so, and it's really almost the speed of how fast the electrons are flowing through the current. Okay, current is brought to you by the letter I, and it is a scalar quantity. Okay, and we can actually calculate current by using charge divided by time. Okay, so this is amount of charge. We know that that's what Q represents. And then we know that delta T is time, or change in time. Okay, so we can calculate the current flowing through a circuit, and it's really the speed of how fast our charge is moving through the circuit over a certain period of time. Okay, so if we want to calculate current, we can do how much charge is moving past one spot of the circuit divided by the time that it takes for that amount of charge to move past it. The unit for current is called the ampere, and some people will just say amp. Okay, and the unit symbol is a capital A. Okay, now, so 1 amp is actually 1 coulomb per 1 second. Okay, so an amp is how much, or 1 coulomb passing by every 1 second is going to be 1 amp. All right, so if we're going to do a couple practice questions with current. So find the current. If 0.2 millicoulombs of electrons pass a point in 0.75 minutes. All right, so for this, we're going to do current is our charge divided by our time, but neither of them are in the unit that we need them to be in. Charge has to be in coulombs, time has to be in seconds. So our 0.20 millicoulombs is actually 0.2 times 10 to the negative 3 coulombs. And our 0.75 minutes, I want to convert into seconds, is actually 45 seconds. All right, so we have 0.2 times 10 to the negative 3 coulombs on the top, 45 seconds on the bottom. And so we're 4.4 times 10, 1, 2, 3, 4, 5, 6, to the negative 6 amps. Okay, so 4.4 times 10 to the negative 6 amps. And if we really want to, we could put that into microamps. That'll work really nicely with 10 to the negative 6. So that's 4.4 microamps. All right. So that's how we calculate current. Now, when we're talking about current in a series circuit versus a parallel circuit, so in a series circuit, current stays the same. And in a parallel circuit, the current is split between pathways. Okay, and again, we're going to talk more about this when we get to looking at an entire circuit. So we're going to look at some larger circuits. And so you just want to put that into your notes in with your current section, just so that we have it down for current. And then we're going to talk about it in terms of the entire circuit as well. Okay, so we're ready to talk about voltage. Voltage is also called potential difference. Okay, and voltage is essentially the work involved when a charge moves from one point to another. So you can kind of think about it as how much energy is associated with moving a charge. Okay, and it's not quite exactly the same thing. It's not measured with joules, but you can sort of think about it in terms of that. So the unit for voltage is actually called the volt. And it's symbolized with a V, but we also symbolize voltage with a V. Okay, so we use V to stand in for voltage, but we also use V as the unit because it's the volt. Okay, if we are trying to calculate voltage, it's actually a difference in voltage, and it's actually a change in energy over the charge. Okay, or it could be the work done over your charge. Okay, and so what that means is that 1 volt is actually 1 joule per 1 coulomb. So when I said that it's kind of like energy, it's not exactly energy specifically because it's energy based off of how much charge. Okay, and so 1 volt is actually 1 joule per coulomb. All right, so we have our formula for voltage. So let's try a practice question. So if we have 120 joules of energy, while moving 52 coulombs of electrons, find the voltage. All right, so if we want the voltage, we are going to have to do the energy or the work divided by our charge, 52 coulombs. So we get 2.3 volts as our voltage here. All right. Now, in terms of voltage in our circuit, so we're going to add our little section here for voltage. So in a series circuit, voltage is split. And then in a parallel circuit, voltage is the same throughout the whole circuit. Okay. Now, again, we're going to talk about this once we get looking at a very large circuit, when we're looking at everything in the circuit at once. Okay, so our last thing that we want to talk about is resistance, and then we're going to be able to look at large circuits together. So resistance is essentially what resistance a material gives to electric charges that are passing through it. Okay, so it's the resistance of the material to the electric charge passing through it. And so that means that every material is a little bit different. So different materials all have different resistances, okay? And so we use capital R. Maybe we use capital R, there we go, to measure resistance. Again, it's a scalar property. It's got no direction, okay? And the unit for resistance is called the ohm. And it's symbolized using a Greek letter. Hold on, I can draw that better. The Greek letter is omega, okay? And so that's the symbol for the ohm. So in words, we would say ohms. But when we're using a symbol, then it's the omega symbol. Okay. Now, resistance and voltage and current are related to each other. And so this is the most important formula in electricity. Current is equal to voltage divided by resistance. Okay? And so this formula we can use in our circuits. As long as we have two, we can find the third. So if we have voltage and current, we can find resistance. If we have voltage and resistance, we can find current. If we have resistance and current, we can find voltage. Okay? It is absolutely the most important formula within this unit because it allows us to find whatever is missing. So whether we're trying to find voltage or current or resistance, as long as we have two out of the three, we can always find the third. All right, so we are actually going to talk about resistors in our circuits. So if we talk about resistors in our circuits, so in a series circuit, resistance is you know what, let's put this in a different spot. I'm going to need a little bit more space in a small little box for resistance. Okay, so resistance in series. So there is a special formula. So if you want to find the total resistance for the whole circuit, then you add up the different resistors that are in the circuit. As long as they're in series, you can just add them together. Okay, so say you have a circuit that has a resistor, and remember that's what the symbol for resistor is, and the circuit's in series. And so we have a resistor that is 10 ohms and 15 ohms, and let's say is another 10 ohms. Okay, then that total resistance is going to be 10 plus 15 plus 10. And because they're in series, because they're in just that one pathway, okay, you're able to just add the resistors all together. Just add the resistances up, and your total resistance is the resistance for the whole circuit. Okay. Now, if you are in parallel, so resistors in parallel, the formula is a little bit different. 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth, for however many resistors you have. Okay, so this looks a little bit different, right? So this is the total resistance now. All right, so say we have our 3 same resistors, but now they're in parallel with each other. Okay, so we've got 3 resistors in parallel. And so we still have 10 ohms, 15 ohm resistor, and then another 10 ohm resistor. Okay, so our total resistance, so 1 over RT, is going to be equal to 1 over 10 plus 1 over 15 plus 1 over 10. Okay, and so the first thing that I would do is to do all of the math on the right. So 1 divided by 10 plus 1 divided by 15 plus our 1 divided by 10. And so that's going to give us 0.2667. Okay, and now we need to rearrange and cross multiply to figure out our RT. Okay, so we're going to get 0.2667 RT is equal to 1. So then RT is going to be 1 divided by 0.2667. So it's 3.75. Okay, so the total resistance for that entire circuit now is only 3.75 ohms. And it's because of how resistance is added or added together in a series circuit versus a parallel circuit. So in a series circuit, we can just right away add the resistors. In a parallel circuit, we have to add their reciprocals. Okay, and that's what the 1 over R1 stands for. And so we have to add their reciprocals in that parallel arrangement. Okay, and so that's how we calculate resistance in a large circuit like that. All right. So we are going to do a practice question with a very large circuit. So I'm going to draw the circuit first, okay? And then with the circuit, you'll be given the resistance, okay? And then we are going to look at calculating the current and the voltage at every section of the circuit as well. So we're first going to draw the circuit. Leave yourself a bit of space because it's quite large. All right. So we've got this battery, and we're going to get to a point where we've got a resistor here, and then a resistor here, and then there's another resistor, and then we're going to turn the corner, and we've got another resistor. Now we're coming to a point where there are 3 resistors. Okay, and then we're splitting off here. There's a resistor up here, and then there are 2 right next to each other here. And then we're going back up to the battery. All right. So with this circuit, we are going to know the resistance for each resistor. So we've got 10 ohms up here. This bottom one is 20 ohms. This one on the right is 15 ohms. And then we have 20 ohms. Then we have 20 ohms here. 15 ohms in the middle and 5 ohms on the bottom. Then we've got 20 ohms, 30 ohms, and 40 ohms over here, okay? And with this circuit, we know that it is 120 volts for the whole circuit. Okay. So the first thing that I want us to do is I want to find the total resistance. So I want to find the resistance for the whole circuit. Okay, so that's the first thing that I want to do. The next thing that I want to do is I want to find the voltage and current at every single little section of our circuit. So where all the resistors are, I want to know how much voltage is going through them, how much current is going through them. Okay, so I want to find the voltage and current at every section as well. So I'm going to start out by finding the total resistance. Now, this is tricky because I have some sections, like at the beginning here with the 10 ohm and 20 ohm, that are in parallel, and some sections that are in series with each other. Okay, so what I'm going to do is I'm actually going to group different sections so that I can get to a circuit that is only in series. Okay, and then I can just add the resistors together to get my total resistance. Okay, so the first thing that I'm going to do is I'm going to use lots of colors here. Okay, and so the first thing that I'm going to do is I'm going to say that this section right up here, I'm going to group that, and I'm going to group those and call that group 1. Because if I can figure out how much resistance is going through the two of those, then those are in series with the 15 ohm resistor and the 20 ohm resistor. Okay, so that's going to be my group 1. So I'm going to just start with group 1, and we're going to find the overall resistance for group 1. All right, so group 1 I know is in parallel, which means 1 over my RT for group 1 is going to be 1 over my 10 plus 1 over my 20. Okay, so then I'm just going to do the math. So 1 divided by 10 plus 1 divided by 20. Okay, and then I have to cross multiply, so it ends up being 1 divided by that answer. So my total there is 6.67 ohms. Okay, so that's for group 1. Now, group 1 is going to be in series with my 15 ohm resistor and my 20 ohm resistor, so I don't need to do anything with those two. But my next section that I need to group is going to be this section here. So I want to collapse those until they're just one resistor, and so I'm going to call that one group 2. Okay, so with group 2, again, 1 over my RT, because this is in parallel, is going to be 1 over 20 plus 1 over 15 plus 1 over 5. So then my total there in group 2, so 1 divided by 20 plus 1 divided by 15 plus my 1 divided by 5 gets me 3. Let's try that one more time. 3.16 ohms. Okay, so that's for group 2. All right, now my next section, I have to look at this section where I've got 20 ohm resistor and a 30 ohm and a 40 ohm resistor. But for this section, I'm going to actually need to use 2 different groups. So let's use yellow. Let's use like a dark yellow for one. Okay, and so this section here is in series, but then it's in parallel with the 20 ohm resistor. So I'm going to name this one group 4. Oh, sorry, group 3. Okay, but then I also still need to do the overall section. So we're going to use like a pink color here. Let's go with this, an actual pink. And so then this whole section here now is going to be my group 4. All right, so first in group 3, so with our group 3, our total is nice and easy because we just get to add them together because they're in series. So it's going to be 30 ohms plus 40 ohms. So it's 70 ohms, okay? And then when we're ready for our group 4, so that's going to be in parallel again. So 1 over our RT is going to be 1 over 20 Let's try this again. Plus 1 over our 70 for the bottom section. Okay, so then our total resistance there. So we're going to do 1 over 20 plus 1 over 70. And so we're going to get a total resistance of 15.5 ohms. All right, so then to do the entire circuit, so this is the whole circuit. Okay, we're going to be able to add group 1, our 15 ohm, our 20 ohm resistor, group 2, and group 4. Okay, so that means group 1 was our 6.67, plus we're adding our 15 ohm and our 20 ohm resistors, plus we're adding group 2 is our 3.16, plus we're adding group 4, which is our 15.5. Remember that we're not adding group 3 because group 3 already got incorporated into group 4. So 6.67 plus 15 plus 20 plus 3.16 plus 15.5. And we've got an entire resistance of 60.33 ohms. Okay, so that means that's the whole circuit. Has an overall resistance of 60.33. Now, we also know that we have an overall voltage of 120 volts. And so we are going to calculate the current. And so we know that current is voltage over resistance. So the current for this circuit is going to be 120 volts divided by our 60.33 ohms. So it's going to be 1.99 amps. And so again, that's the current for the whole circuit. Okay. Now, the voltage for the whole circuit and the current for the whole circuit is not the voltage and current at each individual resistor. And so we're going to go back to our resistor picture, or sorry, for the circuit picture, and we're going to look and see how we're going to be able to calculate voltages and resistances at every single resistor. Okay, so we know now that our current is 1.99 amps for the whole circuit, and we always knew that our voltage was 120 volts. Okay, so just a reminder about voltage and current in series versus parallel. Okay, So current in series is the same. In parallel, the current is split. Voltage in series is split, but in parallel, it's the same. Okay, so if we look at our entire circuit together, okay, we have 120 volts and we have 1.99 amps, okay? Since current is the same through series, that means that the current, I think I'm going to write in green because I haven't really been writing in green. So the current going through this 15 ohm resistor and this 20 ohm resistor has to be the same as the current that's flowing through the entire circuit because those are in series with each other, okay? And so that means that the current here is 1.99 amps. And the current down here is also 1.99 amps, okay? That means we can find the voltage at both of those resistors. And so we're going to find the voltage, and I'm going to write the voltages in blue, okay? We're just using our formula, I is equal to V over R. So when we're trying to calculate the voltages, we're going to use the resistance times the current. So that means the voltage at this 15 ohm resistor is 29.85 volts. And here we're 39. Let's try that one more time. 0.8 volts. Okay, and so we know that voltage is going to get split between things that are in series. And so it makes sense that we don't have the same voltage going through the 15 ohm resistor as we do the 20 ohm resistor. All right. Now, the other thing that we know is that through group 1, we're going to have a current of 1.99 amps. But that is not the current going through each of the resistors. That's the current going through the total of group 1. Okay? The same thing is going to be true for group 2. We'll have 1.99 amps here. But that is not the current that's going through each resistor. That's the current that's going through the total of the resistors. And then the same thing is true happening over here in group 4. We'll have 1.99 amps. But again, that's not the current going through each resistor. That's the current going through the entire section. So if we go back up to group 1, we know that the current going through that whole section is 1.99 amps. And I want to remind you that we know the the resistance through that whole section was our 6.67 ohms. With that, we can find our voltage because voltage is current times resistance. So 6.67 times our 1.99 gives us a voltage here of, I'm going to write voltage in blue, 13.3 volts. Okay, going through that whole section. And we know that voltage through a parallel section is the same. So that means each resistor has 13.3 volts. Okay, and so then we can use the voltage and the resistance to find the current through each section. So if we start with the top resistor, that 10 ohm resistor, our current is going to be our voltage, 13.3, divided by our resistance, which is 10. And so the current going through the top one is 1.33 volts, 33 amps. Now the nice thing is that we know that the total current going through here is 1.99. And so we can actually just subtract 1.33 from the 1.99. And so that's going to be 0.66. Now you could use the voltage divided by the resistance again. So 13.3 divided by 20 is also going to give you 0.66. Okay, so both of them will give you the same thing. All right, so I'm just going to cross out the things that we've used already. Okay, just so that we know that those are not attributed to a specific resistor, but those were attributed to the group. Okay, and we used those to help us find each individual resistor. All right, so if we move down to group 2, okay, so now that we know we have a current going through that whole group, we also, remember, have the entire resistance for that whole group as 3.16 ohms. So we can find the voltage for that entire group. And so 1.99 times our 3.16, we've got 6.29 volts happening through that entire group 2. Okay, and so that means we have 6.29 volts here, and 6.29 volts here, and 6.29 volts here. Okay, so now we have the voltage and the resistance at each resistor. We can find the current. Okay, so we do our voltage divided by our resistance to give us our current at each resistor. So our top one is 0.31 amps. Then we're 0.42 amps. And then we're 1.26 amps. All right, so then we can cross out those values because those were for just group 2, not for each individual resistor. All right, so we're going to go on to our last section. So that's group number 4. So we know that group number 4 has this current of 1.99 amps. And we also know that it had a total resistance of 15.5. Okay, so we can use our resistance and our current to find our voltage. So through this whole section of group 4, we have 30.85 volts. Okay, going through that entire section. Okay, now this section is a little trickier because we have some sections that are in series and some that are in parallel. Okay, so the 20 ohm resistor is in parallel with the 30 and the 40, but the 30 and the 40 are in series with each other. So we're going to start with them being in parallel, and then once we get the 20 ohm resistor, we're going to be able to do the 30 and the 40 in series with each other. So in parallel, we know that our voltage is the same. Okay, so that means that we have a voltage up here of 30.85 volts and a voltage in group 3 also of 30.85 volts. Okay, our current has to be split, and so we can use our formula to find the current through the 20 ohm resistor. So that current is going to be 30.85 divided by 20. So that current, we've got 1.54 amps. Okay, but since we know that 1.99 amps is going through the whole section, that means that through group 3, we have a current of 0.45 amps. Okay, so then we're going to look at the 30 and the 40 ohm resistors in series with each other. So in series, that means that the current has to be the same. So that means both resistors have a current of 0.45 amps. Okay, and then we can use that to find our voltages. So 0.45 times our 30 is going to give us a voltage for our 30 ohm resistor of 13.5 volts. And then our 40 ohm resistor is going to have an 18 volt voltage. Okay, and that's it. So now we have calculated the current, the resistance, and the voltage at every single resistor. Plus we calculated the overall current for the entire circuit, and we calculated the entire resistance for the entire circuit. okay? And really, the only tricky part to this is making sure that you remember these ideas, okay, as well as the formula for how current, voltage, and resistance are related to each other.